In fact, to a certain extent, that's what this class is supposed to be about. It's helping you try to figure out, no, you don't know when someone asks a question, but if you go through and analyze it, you actually can come up, maybe not with the final answer, but something that starts to approximate getting you in the right ballpark. Anyway, what these other students did a few years ago, and it took me a couple of weeks to figure it out, is they were asking me their problems from their other course. We would spend 10 minutes at the beginning of class answering the homework problems for the other course. But I didn't mind. Okay, you ready? Hopefully some of these things are going to be up on the web, but if you're here, you don't need that. But if you do miss class, you can watch it on the web. Last time we talked about bonds, and in fact even van der Waals bonds is extremely high. Primary bonds, covalent, ionic, and metallic, with 1 to 3 electron volts as the binding energy between two atoms that come together at some fixed distance, is going to be on the order of 1 million to 3 million psi. About 1 electron volt per million psi if you just study what it takes to pull the thing apart, all atoms. If this is a plane of atoms, you have to break all of them simultaneously. In the demonstration of a metal that I did for you, basically you're going to unzip it like a piece of perforated paper. You're not going to break them all at once. You're going to peel them apart. And so you're only breaking one line at a time. I mean, van der Waals bonds, back on? Yeah. Van der Waals bonds, which are about 1/10 to 2/10 electron volts, should in principle have a strength of 100,000 to 200,000 psi. Well, that's the strength of a high-strength steel. But in fact, we know that polymers, plastics, don't have anywhere near that strength. We know that metals don't have anything near this strength, except I did mention that iron fibers, iron whiskers, which are little perfect crystals of iron with only one dislocation coming up through the center, called a screw dislocation. When you pull on it in the long direction, that dislocation is lined up, and so it can't move. And you can get 2 million psi in an iron whisker. And this guy Smalley at Rice University has predicted that carbon nanotubes will have 2 million psi. Well, they probably will, if anyone could do a tensile test on them to prove it. The problem is, things don't do that because of defects. In fact, there's a guy who used to be head of materials at General Electric aircraft engines, and he once said, materials scientists think that structure controls properties. Metallurgists know that defects control properties. Just like a second ago, when it wasn't on the videotape, I pulled the paper apart. When you put a defect in there, you control the strength of the material by the defects that are in the material. Okay, with that, we know that two atoms coming together, they want to condense. If they want to condense, they're going to have an energy distribution function that looks like this. As they come together, they can lower their energy, go to a lower energy state, and bond together. So I'd have an atom here, and I'd have an atom here, and that's the interatomic distance. And this is the force. When the force of attraction is 0, or attraction and repulsion, that's attraction, that's repulsion. An atom out here will be attracted to an atom over here, and it will be repelled if you try to squeeze them further together. In fact, there's some interesting things. The property of the material, that's got to be the bulk compressibility, the slope of that, right? How hard do you squeeze on something to compress it? That down here, this curvature, the second derivative, or the curvature, which is the second derivative, basically is that same bulk compressibility, because this is just the first derivative of that. Okay, so you can get the modulus of the material from these types of curves. I mean, this is, you're getting back to the fundamental physics of what brings two atoms together. Now, if atoms that are solids have such a strong attractive force, why don't they stick together? When I throw a piece of paper on the table, how come I can pick it back up again? Why didn't it bond to the table? Obviously, atoms are touching each other, right? Now the question is, did you read chapter 16? Okay. There's two reasons, two fundamental reasons why, if you just touch not metals necessarily, two materials together, they don't automatically stick together. Contamination and
surface roughness.
Surface roughness. Okay. So contamination and surface roughness, we're going to talk about those things for the next couple of weeks in various ways. But let's just write them up. If you learn certain correct principles about science, you can figure out a lot of the other stuff for yourself. That's one of the points of this course. And it goes all the way through. We're going to do cold welding today. We're going to go through soldering and brazing and adhesive bonding and friction welding and a number of different things, and actually even to fusion welding. And it turns out somehow you've got to overcome these two things. Now, why do you have to overcome them? Well, it turns out that in the real world, we do have examples of times when you stick two things together and they do bond. And in fact, I often say that the science of welding is the opposite of the science of lubrication, or the real name for the science of lubrication is called tribology, T-R-I-B-O-L-O-G-Y, which comes from a Greek word that means surface. Okay, so tribology is the study of surfaces. Welding is I'm basically trying to stick two surfaces together. Okay, it turns out that historically, the first Mercury space flights, they lubricated, in Alan Shepard's Mercury module, they lubricated things with graphite, and people know graphite as a lubricant. And this is the structure of graphite. It's hexagonal close packed, for those of you who know anything about materials. If you don't worry about it. But basically, the carbon atoms, you can tell this is carbon black, right? The atoms line up in planes. See that? And on the top, they have a honeycomb type structure. That's the hexagonal close packed. So here's hexagonal and close packed just means that they, each one of them has 12 nearest neighbors, for whatever that's worth. And those 12 nearest neighbors basically mean you can't get, of equal sized spheres, you can't pack things any tighter than 12 things around each other. If you take a penny, 7 pennies, and you can put 6 of them around another, right? If they're all equal sized circles. And then you can put 3 on top of that, and then you can put 3 on the bottom. And there's your 12 close packed around that 1 penny sitting on the table. Okay, so turns out when Alan Shepard and a few other people first went up in, what was it, 1962 or whatever? Anyway, early 60s. They had lubricated things with graphite. You can go to the store and still buy graphite as a lubricant for locks and things. You just squirt a little graphite powder in the lock. Well, it turns out when they got up in space, or rarefied atmospheres up above us, it was no longer a lubricant. Turns out graphite, in the absence of oxygen, becomes an abrasive. And that's not so hot when you're trying to make this spacecraft work, when things start sticking together. And the reason is, it turns out carbon-carbon bonds we know are extremely strong. This Nobel laureate Smalley at Rice University is going around telling everybody that carbon nanotubes will have 2 million psi strength. And what he's discovered is carbon-carbon bonds are very strong. They're not the strongest bond. The strongest bond is silicon-oxygen bonds. Silicone backbone polymers, okay? But in any case, they are among the strongest bonds, the carbon-carbon bonds. And so why shouldn't the bonds here stick to the ones here? It turns out that what happens is we know that carbon has a strong affinity for oxygen, and oxygen in the air at 1 atmosphere pressure, or actually 1/5 of an atmosphere pressure is what the oxygen pressure is in the air, will essentially line up on some of these basal planes of the graphite, and it will, now I have a satisfied surface. I don't have a high energy unsatisfied carbon bond that wants something because it's now bonded to oxygen. And a carbon-oxygen bond is a satisfied bond. Okay, carbon monoxide or carbon dioxide can satisfy the free electrons on a carbon molecule or a carbon atom. So what happened is NASA got to be very, very interested in surfaces and cold welding of these things. I had a 13A student back in the early 80s, and we were welding titanium in a glove box, and we had the glove box down to like 10 to the minus 16 atmospheres of oxygen, and he had a little vacuum cleaner to clean up the welding fume and other stuff in the glove box, and he found that the motor in the little vacuum cleaner would wear out, the carbon brushes would wear out in like 5 minutes of use. So, we had a little wet, one of those little hand vacs inside the glove box. And he came to me and says, it's wearing out, and I have to keep replacing these things. I said, well, go use molybdenum disulfide. Change your carbon brushes to molybdenum disulfide. Molybdenum disulfide has the same crystal structure, but instead of oxygens, it has sulfur. You have molybdenum atoms and you have sulfur, and molybdenum disulfide is a very good solid lubricant. And it turns out if you put it in a rarefied vacuum, you won't suck the oxygen off. But you can suck the oxygen off of some of these things. So, in any case, NASA went out and this is in your bibliography, but this is the book. It was dated. This is Adhesion or Cold Welding of Materials in Space Environments, 1967 conference by the American Society of Testing and Materials. Why 1967? Because the first couple of Mercury shots up there, they ran into these problems. Then they had to send everybody out to do research on them, fund a bunch of contracts, and here's the symposium where all those people came back together. And they talked about, in a rarefied atmosphere, what it takes for two mineral particles to stick together and all kinds of things. You've got some references in there, but basically lubrication breaks down when you clean the contamination off the surface. Graphite's a lubricant because in this case oxygen is the contaminant on the surface. It satisfied the bonds. Ordinarily, if I have a primary bonded structure, let's say these are carbon atoms, they're bonded to other carbon atoms in the structure, then this thing goes on in all directions, except at the surface, I have these unsatisfied bonds. Carbon wants to have 4 bonds around it. Its valence is 4, and I'm going to have unsatisfied bonds on the surface. Those unsatisfied bonds have a higher energy than if they were satisfied. Remember, when you get a bond, you end up with a lower energy, right? If I don't have a bond, if I got one of the 4 bonds missing on the surface, it's not completed, then I'll have a higher energy state, and that leads to a phenomenon called surface energy of materials. Now, surface energy is equivalent to surface tension. It turns out surface energy has units of joules per meter, and surface tension has units of newtons per square meter, which turns out to be the same, right? Because a newton meter is a joule. So you can think of surface energy and surface tension as either an energy, or you can think of this surface lack of bonding as either an energy or a force. Sometimes, like if I'm thinking of little bubbles that I'm forming, I can think of it as a tension. Other times, I want to think of it as an energy. Nature wants to lower its energy. It can lower its energy in graphite by putting oxygen to partially satisfy those bonds on the surface. So if I were to take something, a perfectly clean material, and people have done this type of experiment, and they can do it in an ultra-high vacuum. They can cleave a material. They can take a sodium chloride crystal, which is a brittle material, and they can cleave it in a vacuum, 10 to the minus 13 atmospheres or something. And if they stick it back together, when there's no contamination on the surface, it will bond with almost its original strength. Maybe 10% of its original strength. Okay? Not its full original strength. Because contamination is not there. It turns out there's something, if I look at something called the Langmuir, Irving Langmuir was a physicist at General Electric Research Labs in the early part of the last century. And he was a great surface scientist. The Langmuir is now, is 10 to the minus 8 atmosphere seconds. And I gave you a handout in your stuff that comes out of this adhesion cold welding in space. And it's just a single sheet. Just to let you know, it looks something like this. Okay, it's just a one-dimensional graphs going across here. And it has the apogee of Sputnik 1, sea level pressure, altitude in feet. As you go up, the pressure gets to be less. And they have time to form a monolayer, the very last line. Time to form a monolayer at 25 degrees centigrade. Well, the monolayer they're talking about is if I were to somehow magically make a perfectly clean surface, how long will it take for enough atoms in the gas surrounding it to contaminate the surface? And that number is the Langmuir, which is actually, it says 5 times 10 to the minus 8, but anyway, who cares? It's on the order of 10 to the minus 8 seconds. So if I want to pull two things apart, what I used to do is I break a piece of chalk. Okay? I break the chalk, if I stick it right back together, and I do it quick enough, it will bond together. The problem is I have to do it within something less than 10 to the minus 8 seconds. So I didn't quite do it quick enough. I'll try it again. And that's why if you do this experiment at 10 to the minus 13 atmospheres in a super vacuum system, and that's about the best we can do. I'm not sure we can, maybe 10 to the minus 12 is the best we can do on Earth. Intergalactic space is like 10 to the minus 16 atmospheres. But at 10 to the minus 13 seconds, well, I've got 10 to the 5th seconds. 100,000 seconds before I stick those things back together. So I could break the piece of chalk in a vacuum system with an ultra-high vacuum and then put it back together. And my only problem at that point is not contamination, because I've satisfied the bonds, but it's surface roughness. The chalk ended up with a rough surface. Can I put them back together with perfect atomic registry? And of course the answer is no. But in fact, if people do these things in a vacuum system, they have been able to put special super flat foils back together in a vacuum system and get about 20 to 30% of the base material strength. And it's only the surface roughness that's the inhibitor. Okay? So contamination is something, in lubrication, you're trying to contaminate the surface. Okay? It turns out graphite at atmospheric pressure, you've always got oxygen around, unless you happen to be like Dan Rees, who basically ended up in an argon atmosphere with no oxygen, and his little brushes in his motor in his glove box didn't work, right, because there was no oxygen. But ordinarily we have oxygen around, and graphite works because it's automatically of oxygen in the atmosphere. Why do I put oils on things to lubricate them? Because those oils help provide the surface contamination. And in fact, if you go to a lubrication book, you'll see people draw ligands. If any of you have studied biology, you're familiar with ligands, they tend to draw the molecules like that. And here's a surface, and they show essentially a head of the molecule that wants to bond to the surface, and then it ends up with basically a carbon chain that kind of floats in the air. So it's kind of like grass growing on the surface of something. Typically stearates, soap, or oleates. If you go to organic chemistry, you'll find these are just different length carbon molecules. I think stearates are like carbon 18 or carbon 22, and oleates are around there. Fats, basically. It's been a while since I've done this, but if you go back to the different types of stearates, stearic acid or oleic acid, they basically all have a name that represents a certain number of carbons, kind of between like carbon 12 to carbon 25. So you basically got little polymer fibers sticking up from the surface, carbon-carbon bonds. And some of them, if you go back to why they call it a stearate or oleate or a linate, linseed oil, well, it turns to linseed oil tends to produce fats with that number of carbons in the chain. One of them comes from the word for sheep, because sheep fat has a certain number of carbons, or has a high propensity of 16 carbons, or whatever the number is. Okay. So they tend to be fat molecules, which are nonpolar on one side, or polar on one side and nonpolar on the other side. The polar bond tends to stick to the surface, and the nonpolar bond is one that's fairly stable and gives a low energy surface. No interest in forming further contamination, no interest in forming a bond or a weld. And that's why lubrication is the opposite of welding. Is lubrication, I'm trying to intentionally contaminate the surface. In welding, I'm doing everything I can to prevent the contamination or to eliminate it in some way. Any questions on any of that? Yeah.
Question on your equivalence of surface energy and surface tension. So if the surface has high energy, that implies that it's ready to bond with contaminants.
It's going to bond better.
It'll bond better with contaminants, but is that true of high surface tension? It's going to.
Yes.
So a substance, a material that has high surface tension is going to tend to bond better with contaminants?
It's going to be easier to bond it. It may be harder to clean it. Okay, that's maybe where your kind of your thinking is kind of going around circular. It's harder to clean the contamination off of something that wants to have a high surface energy because it's bonding that contamination more tightly. But if you can get it clean, it will bond better. So it turns out that if I go back to my thing before, things with primary bonds, if they're clean, will give me the greatest strength. And we're going to find in soldering, for example, metals which have primary bonding are easily contaminated immediately with oxides on the surface from the air. 10 to the -8 atmosphere seconds. Well, maybe not every oxygen molecule that hits, and not every molecule in the air is oxygen. Some of them are nitrogen, which cannot react with all metals as easily. It might take 10 to the -7 seconds, but who cares? I still am not fast enough to put that piece of metal back together. However, in soldering operation, I put flux on or something else to clean that oxide off. That metal now has a high energy surface, and if I can get some other liquid to flow on there to help satisfy those bonds, I can bond it very, very readily. Now, why is Teflon such a good lubricant? Because on the surface of Teflon, I basically have a covalently bonded structure, but all the bonds are satisfied. Teflon has the lowest surface energy. It's more difficult to bond a polymer that has a surface of van der Waals bonds. Adhesives don't stick to Teflon very well. Okay? Teflon's a non-stick surface. Even eggs don't stick to it. Right? And we're going to find later that a lot of your adhesives are just proteins. Okay? Because proteins tend to have the same type of structure like this. In fact, the cell wall, if any of you study biology, the model of a cell wall is nothing more than a bunch of proteins facing each other. Okay? You have an outer surface of the cell wall and inner surface, and this is what the biologists are studying all the time now, is how things get through the cell wall, how molecules get through. But the cell wall is a double layer of these, like taking two pieces of astroturf facing each other with the grass growing, right? Yeah.
How do they specific Teflon to stick to the pan?
Good question. We're going a little bit ahead in the course, but it has to do with mechanical interlocking. You roughen up the surface. You abrade the surface so you end up with a rough surface, and you get a mechanical interlock of the plastic on the metal. If I tried to stick Teflon on a nice shiny piece of metal, it'd peel right off. I mean, how do I get adhesion of paint on a piece of metal? I roughen up the surface. There's various ways to roughen up. We're kind of getting a week ahead in the lectures, but that's okay. I can roughen up the surface. My oldest son's Eagle Scout project was to scrape the paint from a building that was only a year old on the outside handrails and the lighting fixture and stuff. It was just all peeling off. It was galvanized steel, and they just painted it. They didn't put a primer coat on. Well, the primer coat of paint actually usually has something, a chemical in it, that chemically reacts with the surface of the steel or the aluminum if you get Rust-Oleum. In this case, they hadn't primed it, and they just put the other layer of paint on, which didn't, the outer layer, which didn't have this thing that was going to chemically react to form a rough surface. So we had to go sandblast and scrape and get all the Scout stuff doing that. And then I made Matthew research, what do you do for galvanized steel, okay, which is just zinc-coated steel. Turns out, on galvanized steel, you can roughen up the surface by acetic acid to form a zinc acetate, which is a chemical reaction. And so I got some, we could have taken vinegar, but I could go to MIT, use my personal account, buy a gallon of acetic acid, and we could dilute it. So the first week we scraped everything. The second week I had the boys out there, Matthew had them out, but let's face it, who does these things, right? We had them out there painting acetic acid on the handrails. And as that dried off, we put the primer coat on. And the third week, we came back and put the final coat on. That stuff now, I mean, everything was just peeling off after 1 year. 15 years later now, I go and I look at those handrails, and the paint is still adherent, and the paint is worn back down to the galvanized, but it's worn down, okay? Nothing's peeling off, because I had a very rough surface. So getting back to your story on how do you bond the Teflon, I did some consulting a few years ago for Farberware. Makes Millennium cookware. These really expensive Teflon-coated pots. They plasma spray on the inside of the pot a powder which is very porous, and so you end up with this very, very porous internal surface. And then they impregnate that under pressure and essentially melt the Teflon into all those pores, so it's mechanically interlocked. It's not a chemical bond; it's a mechanical bond. Okay, so you roughened up the surface. If I want to get better paint adhesion on aluminum, I anodize it, because if I anodize the aluminum, I form a little porous oxide skin, and it's going to be mechanical interlocking on the aluminum. If I want better paint adhesion on steel, I phosphate it. Basically, I put it in Coca-Cola. Coca-Cola is phosphoric acid with a few other things in it, but not much. It's mostly phosphoric acid with a pH of about 2.3. Excellent cleaning solution. In fact, they got a rusty panels down here at the New England Aquarium, and sometime in the next couple of weeks we're going down to clean the rust off the stainless steel panels at the New England Aquarium to see what they can do to clean it. We're going to use citric acid, which is orange juice, and we're going to use Pepsi Cola because I'm the consultant to the aquarium. The consultant, Professor Lieutenant, is the consultant to the people who built it and have the warranty on it and have to fix this. But they did some tests. Professor Lieutenant's people did some tests. Pepsi works better than Coke as a cleaning solution on stainless steel. So it's not as if those other things in there don't do something. They do add value. Okay. So does that answer your question on Teflon? Mechanical interlocking. And so we've covered part of the adhesion lecture later. So anyway, we get these types of surface structures with contaminants, and most of what we're going to try to do in welding and joining, which includes adhesive bonding, soldering, cold welding, and everything, is try to remove the contamination and do something, because when I actually stick things together, they are rough surfaces. It's mountain peaks. And something might look smooth to you, And you think that they all touch very well, but in fact, on an atomic scale, they look like this. And you stick them together, and they only touch a few spots. In fact, one of the questions is, how large an area do they, what's the largest area you can get in sticking these things together? So, pass that back to its back. In terms of getting rid of surface roughness, well, before I do that, let me while you're passing those out. This is another handout that you have, and you don't really have to worry about it. This comes out of a book called Welding Processes by Peter Holcroft, who's technical director of the British Welding Institute, which is one of the world's premier places where they study welding and joining. And people have tried to classify welding and joining processes. I think I mentioned yesterday that the American Welding Society lists 199 different welding and cutting processes. In this little thing that he has welding process classification, he has shielding method, and then he has sources of heat, of which some of these things are, he has no heat, well that's not a source of heat. He has mechanical, well it can be heat or it can just be squeezing. He has thermochemical, electrical resistance, electric arc. Shielding is basically a way to try to keep the contamination away. If I look at this axis, and this axis, source of heat, is a way to try to help make it so that I can get better physical contact. If I apply pressure, mechanical pressure, if I apply heat and soften these asperities, these little mountain peaks, I can get a larger area of contact, right? So in a sense, Peter Holcroft didn't think about it when he put this chart together, and I don't find the chart all that useful except to point out to you that basically one axis is how do you control contamination, and the other axis is how do I get control surface roughness. Okay? Lots of different ways to do it. But when he tried to categorize it in the graph, I doubt that he was thinking in terms of surface roughness and contamination. In fact, I think he was thinking of shielding gas and sources of heat, which is what he said, right? Probably a better guess. But in fact, if I go back to the fundamental physics, those are the two things that I've got to do. Now, this handout I just gave you says, okay, how much area of contact can I get? If I just lay this thing gently on itself, and ordinarily the surface roughness doesn't have such a nice regular array. Obviously, if I intermesh these things, I can get pretty good contact, right? But in the real world, they're askew. If I just touch two things together, I will have what I call asperity contact. These peaks are called the asperities. And each one of them will have a slight deformation depending on the weight on this thing. If I throw a book on top of it, I'm going to get greater deformation of those things. If I take something that is a piece of metal and I squeeze on it hard enough until the whole bulk metal starts to deform, can I get 100% contact area? And the answer is no. And that's what the handout is. And the reason is, if I just took two pieces of material and had them press against each other in a compression test, they would both mushroom and deform, right, as I squeeze them together. And that would be the yield strength of the material, because I'm basically just deforming the area right there at the surface, at the interface, right? And that's what I measure as the compressive yield strength. However, if I have a punch, a surface asperity pushing against a solid object, it turns out that the indentation strength is about 3 times sigma yield. This is basically what we call a hardness test in metallurgy. You take a punch, a little pinprick, and you push it into the surface and you find out how deep it goes. Why does it take 3 times as much force to indent a big flat object with a small punch as opposed to 2 small things indenting things in equal area? Because look at it. The material here tends to have to push aside the material over here on the side, right? And the volume of material on the solid that's being deformed by this is about 3 times as great as the volume that's going to be deformed on the narrower punch. that make sense? I've drawn this for any of you that are mechanical engineers as what's called a slipline flow field. And a slipline flow field has these three triangles and these are arcs, and it shows that the flow of the metal through here would be something like that. And you'd end up bulging the material out on the sides, right? If you push this in. Well, it turns out that volume is about 3 times that volume. The amount of force times the distance work that you do in this type of deformation is about 3 times that. In fact, in the slipline flow field theory, it's not 3 times, it's 1 plus pi over 2, which is equal to times sigma yield, which is 2.57. Okay? But that assumes non-work hardened material. So if any of you are really interested in slipline flow field theory, it's the way you study deformation of materials. Essentially, what I've then done, using that type of knowledge, you go through, and where's my copy of that? Okay, here's a copy. Of that contact stresses that we're talking about. If I were to just study the thing on the top there, macroscopic deformation of 2 solid objects, I would find that the load applied, PA max, is equal to the yield stress, which is just the force divided by the area. And that's the macroscopic force. If I now look on a microscopic scale, where I actually have asperity contact, and I want to know what is, I know what the force to deform those asperities are. There's something close to the hardness test. And so it turns out the average pressure is going to be about 3 times sigma yield, or S yield. Okay? I originally did this for some people, a lot of mechanical engineers, they like to use S. They haven't learned the Greek alphabet over in first 2. Metallurgists don't like to use sigma. Anyway. But that's the same force divided by the true area of contact. Not the apparent area, which is this. The macroscopic is the apparent area, you know, length times width. The true area is the area of contact on these little asperities. And it turns out, if you go through all this, because of that factor of 3, if I actually take pieces of metal and squeeze them together until they're macroscopically deforming, and I can't squeeze any harder than that, right? I will only get about 30% contact area, 1/3 contact area. And that's what's on the sheet. Everybody follow that? So what does that mean? Well, that means that the surface roughness problem I can't solve by just straight downward normal contact forces. Okay? I can't just squeeze things together, even in the absence of contamination, and get a good bond. Well, why are we interested in cold welding at all? Well, one of the reasons is, will anybody have an idea why we're interested in cold welding? There are more cold welds made in the world than any other kind. Yeah.
Because when you hot weld and change the properties of the material, for example, if you have some, I don't know, some special steel when you weld it,
Yeah.
the carbon precipitates out, and you change the properties of the actual material near the joint, and lose strength.
That's right, and we'll get to friction welding where you actually do it when you're hot. Actually, I was thinking kind of from a practical point of view, why am I interested in industrially in cold welding? It turns out it's cheap, and we make more than anything else. Because in the semiconductor packages, when I passed around the little semiconductor chips, there's 360 gold wires making a contact to each one of those. They're gold wires that are only 1 mil in diameter. 1 mil being about 1/3 of a human hair diameter. 1/10 the cross section of a human hair. 1/1000th of an inch. Human hair, depends on whether you got thick hair or thin hair, but it's on the order of 60 to 80 microns in diameter. These gold wires are about 20 to 25 microns in diameter. Very fine, and it's basically called thermocompression. Well, actually, they often apply a little bit of heat, but they're gold wires. And here's a picture of one. But here's the gold wire, and it basically just squeezes into the surface until it mushrooms on the bottom. Now, how many of these do I make in a year? Well, I didn't estimate this. And this is, again, we got to figure out how to do these estimates. how many let's say there's 100 bonds per chip. Now, if I'm talking, we'll get to bonding and microelectronics later, when we get a little bit later, but a Pentium might have 300 to 400 bonds around the perimeter. And people would like to get 2,000 bonds on some of these chips, but there's some limitations, and we'll talk about that. Nonetheless, but a memory chip is not as complex. It doesn't have, Pentium 4 has 42 million transistors. And so to access all those 42 million transistors, you need 400 leads coming in. A memory chip may have lots of transistors, but it's kind of a nice regular array, and you may only need 100 bonds per chip. So per chip, you need 100 bonds. Actually, that's only 50 leads, as far as that goes, because you've got 2 bonds per wire, each end of the wire, right? Now, I know that the semiconductor industry is about $100 billion a year. And I know that a chip, on average, now, again, I got a problem in that Pentiums cost a few $100, but memory chips are $2. So let's just say the average chip costs $10, because I make a lot more memory chips than I do Pentiums, right? So if I do all this, I get something on the order of 10 to the 12th bonds per year. And every one of them better be good or the chip doesn't work, right? So that's one of the reasons I'm interested in cold welding, because it's essential for the microelectronics industry. Why do you think they use gold wire? Anybody have an idea?
Doesn't contaminate.
Doesn't contaminate with oxygen, exactly. Of the metals that are found in nature, in the metallic state, you've got gold, platinum, and copper. Now it turns out copper does oxidize, but copper can form an oxide that is protective enough that if you go find native copper, you can pick it up, lake copper in Michigan, just out off the ground, okay? It'll be black oxide, but over time, it can last a million years, okay? Copper can last a million years without just completely oxidizing away. Iron doesn't, it wants to go back to iron ore, iron oxide. Gold doesn't have a surface oxide problem. In fact, about the only thing gold will react with, well, the only elemental anion it wants to usually work with is chlorides or halides. Okay? What is aqua regia, which dissolves gold, is hydrochloric acid and nitric acid. It's basically the nitric provides an oxidizing environment, and the chlorine does the oxidation. And you form gold chlorides, which can be soluble. There are also more complex things like cyanides. Gold cyanide is very soluble. If you ever work near a gold mine, lots of cyanide problems. In any case, gold does have a problem, and that gold does have a high energy surface. It's a primary bond. And so it gets back to your point of, why doesn't gold want to bond? Gold does want to bond to something else, but it turns out there's moisture. There's not only moisture in the air. Maybe gold doesn't form an oxide, but it will pick up moisture and it will pick up oil. Where's the oil in the air come from? It comes from you and me and the trees and the plants. We're all giving off. We're just all raining out oils all the time. Okay? When we sweat, there's oils in our sweat. Okay? So there's always oils in the air. And everything, these metals, gold in particular, love to absorb a little bit of stuff. But it's a very, very weak van der Waals bond, and with about 200 or 300 degrees of temperature, you can basically boil off the water, and you can get rid of the grease. And so we actually do, usually, well, not always, a lot of the gold wire bonding, where you just take gold wire and push it, just ram it into a surface, and form this bulb on the end as it deforms. Okay? We often call it thermocompression bonding because they often do it at a couple of 100 degrees, only to get rid of the contamination. How do they get rid of the asperities and get the good area of contact? Well, if I go back to this guy, this picture in here, The cross-sectional area of this thing is about 10 times the diameter of the thing. It's got about 60 to 80 microns wide as the pad that I squeeze out. And what have I done? I created a tremendous amount of shear. Okay, I just tore the mountains down by shearing them apart. Okay, I could squeeze like this with a straight normal force until I'm blue in the face. I'll only get 30% area contact. If I want to use a mechanical way of getting rid of the surface roughness, I need shear to break things down. And I need to do something to get rid of the contamination. The way I get rid of the contamination in thermocompression bonding for semiconductors is to use gold and a little bit of temperature. Gold and a little bit of temperature just drive off the stuff. Now, other things we'll do, we'll talk about friction welding tomorrow, where I basically squeeze the things together and I actually deform the material and exclude the contamination you can see on these things. I just pushed it aside as these things are rubbing together. And I was using heat to make it deform. And I'm using shear to break down the things. So I'm using the same principles as thermocompression bond, except I'm using a lot more heat, which is kind of the point you were making. So I actually do both. Sometimes it's cold welding. This is hot welding, but it's a mechanical weld where I exclude the contamination by just squeezing it out of the joint. In other cases, I use gold as my bonding surface to get rid of the contamination. However, it gets more interesting because the second best material for making these 10 to the 12 semiconductor bonds is not gold, or after gold. The second best material is gold, after gold. It turns out to be aluminum, which has one of the most tenacious oxides. Okay? So we'll talk about that tomorrow, about why aluminum is second best.